Hi. So today we're doing the first of the review sessions, first of the two review sessions. It's going to be, this final review session will cover storage, indices, SQL, and query execution and optimization. Got it? So I'll begin with, so remember, at the very start of the year, we talked about sorting and hashing, external sorting and external hashing. That's one of the ways we can say answer an order by clause in our SQL query, or if we need to do some kind of aggregation, for example, counting all the instances of some column. We will be using sorting and hashing aggregation operators. So, if you still remember this from the very beginning of the year, one of the first algorithms we went over was external merge sort. And the idea behind external merge sort is if we have a bunch of data that we have to sort, we're going to divide and conquer this data. We're going to sort runs of these data, we're going to make sorted runs of this data, and we're going to gradually, recursively merge these sorted runs. So let's start off with the two-way external merge sort. So in this example, remember, we're reading from disk, and we're going to have two buffers that are reserved for input. So we're going to reserve two buffers for input, and we're going to gradually merge the contents of these two buffers into an output buffer. Whenever one of our input buffers is depleted, we'll grab another buffer from disk, and whenever our output buffer is full, we're going to write that to disk. And we're going to keep doing this until we've merged all of our data. So you can imagine that on each pass of this two-way merge sort, the number of runs we have at any point, the number of sorted runs we have at any point are halved. Any questions so far? Okay. So this is what it would look like if we had 7 sorted runs and we were to perform external merge sort on these runs. So notice after the first pass, we create 4 sorted runs, each 2 buffers long. After the second sorted pass, we have 2 sorted runs, each 4 buffers long. And finally, after our third merge pass, we have 1 buffer, 1 run, 8 buffers big. So these are the 3 passes of a two-way external merge sort. Right? To come up with our runs in the first place, the runs you see on the far left, this 1, 2, 4, 3, 5, 6, 8, 7, those runs, we'll also have performed some kind of sorting algorithms on those runs. And that's pass 0 of our external merge sort. So on pass 0, we create sorted runs, and on each successive pass, we merge these runs together until we're done with one giant sorted run. If we generalize external merge sort, since we have more than just 3 buffers, we can actually utilize our extra memory to merge more runs at any pass, in any pass. So if we have B buffers, that means we can have B-1 input buffers. And that means we can merge B-1 runs at a time. So here are some questions. So if we generalize merge sort if we perform generalized merge sort with B equals 3, it's not the same as a two-way merge sort. Does anyone remember the answer to this question? This was on the first midterm review. Sure. Yeah, we can use the extra buffers after doing. So on pass 0, remember when we were creating those sorted runs, we needed to sort all the data in those runs, and having the extra buffers in our generalized merge sort means we can make runs that are a lot bigger. Yeah. So on pass 0 of our external merge sort, we created sorted runs. And the size of these runs is going to be determined by how much data we can fit in our memory at any point. So if our memory is B pages big, we can fit B pages of data in memory. And so we can sort B pages at a time. And so in that case, we can create larger runs on the 0th pass of our merge sort. Yeah. So two-way merge sort, remember, is only going to be using those two buffers for sorting. Yeah. Okay, so the I/O cost of our external merge sort is now 2n, where n is the number of pages in our file, times the number of passes. Why is that true? Yes. So the answer is, on each pass of our merge sort, we're reading memory, or we're reading data from disk, we're merging it, and then we're writing that back to disk. That one pass constitutes reading all the data and rewriting this data. Okay, so how many passes do we do? Well, if we have n pages and we merge b minus 1 runs at a time, we have one pass for pass 0 where we create our runs, and then we have log of b minus 1, log with base b minus 1 of n divided by b pages that we're merging. So that's how many passes it takes for us to fully merge. So in 2 passes, in this case, the largest file we can sort is b times b minus 1. B pages for the 0th pass, b minus runs merged for the 2nd pass. And in our 0th pass, there are many different ways to perform internal sorting. For example, quick sort, heap sort, or even tournament sort, which you saw briefly in lecture. Any questions? Any questions about merge sort? Okay. All right. So hashing. So external caching is another kind of divide and conquer algorithm. And in this case, there's 2 phases again. The first phase, we divide our data by hashing it up into partitions. And in the second phase of the data, we complete our hashing by rehashing these partitions and performing our aggregation. So external hashing looks a lot like the opposite of external sorting. We take our input in our buffer, in an input buffer. Our buffer is b pages big, and we create b minus 1 partitions. So we have b minus 1 output buffers, 1 per partition. And in this phase, we take our data, we stream it from disk, and we divide it into each partition as we process our file. Afterwards, for each partition on disk, we stream that partition back through our buffer and rehash it in our in-memory hash table. And this only happens if our partition is big enough to fit into memory. Remember, our memory was B pages big. So if our partitions are larger than B pages, then we'll have to recursively hash this data until our partitions are small enough to fit in data. So one of the things you have to keep in mind with external hashing is that you're using hash functions, and hash functions aren't, as you may have learned from 61B, aren't always perfect, right? If we have a perfect hash function, it uniformly distributes whatever we're hashing into our partitions. But this might not be the case, right? And it might not be the case that all the partitions we make are perfectly the size we want them to be. So it could be true that we can have less than b times b minus 1 pages in our input, and we'll still have to make a recursive hashing pass. More about these aggregation operators. There's also this concept of double buffering, where instead of having to fetch the whole buffer from disk once a buffer is depleted, we have another buffer fetch that data from disk in the background, so that at any point when we need more data, we can just switch buffers. And you can imagine a similar scheme for our output buffer. Okay. Any questions about these aggregation operators? External merging, external sorting? Yeah. So remember, okay, so external sorting, you can think of it as being extremely kind of stable in a sense, right? We're always going to sort everything, and unless our tournament sort, so if we're using tournament sort, it could be the case, remember, that our runs are larger than B pages long, right? In expectation, they're actually, I think, 2 B pages. So sorting, but other than that, the number of merge passes we have to perform is pretty constant, right? Not independent of the data. Whereas hashing has a variable runtime, as you've seen, or has a variable I/O cost, right? If we have to recursively hash a partition, then that's going to, of course, incur more I/Os. We're going to have to reread that partition and then rewrite that partition to disk. Any more questions? Okay. Hash aggregation. So in the first phase of hash aggregation, we read our input from disk and we hash these into different partitions. If any partition is too large after this phase, due to our data being too large in the first place or bad luck, then we'll have to take each partition that's too large into memory, and we're going to have to recursively hash each of those partitions. And so you can imagine worst cases for a hashing algorithm in which we'll have to do this many, many times. And then external hashing will, of course, perform worse than external sorting. Okay. Joins. Okay. So remember, so joins are one of the big things we talk about in this class, especially with respect to query optimization. And a big part of query optimization is figuring out how to do these joins intelligently. So remember we had this toy example from lecture where we had 2 tables, sailors and reserves, and we're trying to join them on a column, sailor ID. And so the first simplest join you might think of is a chunk nested loops join. And at the very smallest level of granularity, we're going to be joining tuples together. So for each tuple in our outer relation and for each tuple in our inner relation, we're just going to check if the join predicate matches. And if it does, we're going to output it. So we're going to take each record in R, each record in S, and we're going to iterate for each record of R, or for each record of S, we're going to iterate through each record of R, and we're going to output it if the predicate matches. But remember yes. This is simple nested loops join. Yeah. Yeah. So in general, I'm I'm talking about chunk nested loops join, but yeah, you're correct. This algorithm is exactly simple nested loops join. I'll edit this later to clarify. But yeah, this is simple nested loops join. Going through each and every tuple in our relation, that's simple nested loops join. Yeah. Okay. Any other questions? All right. Okay, chunk nested loops join. All right, so or page nested loops join. So remember the unit of disk I/O is the page, not the tuple. So if we fetch a tuple from disk, we're going to have to fetch the whole page. So we're going to optimize simple nested loops join just by fetching pages at a time. So if we fetch each page at a time, then in this case, instead of fetching each tuple of S and matching it with each tuple of R, we're going to fetch every page of S, and we're going to merge that with every page of R. Or we're going to join that with every page of R. Okay. Everyone clear on page nested loop? Page-oriented nested loops join? Okay. Finally, if we can join by the page granularity, why don't we use the rest of memory and join by chunks? And chunks in this case are going to be the biggest chunks of pages we can fit into memory, while having, remember, an extra 2 buffers to perform the joining. So our outer relations is Sailors, S, and we're going to read that into memory in chunks. We're going to read them in chunks of B minus 2 at a time, and we're going to have an extra input buffer used for streaming pages and reserves through memory. And as we create this join output, we're going to write it to some output buffer, and we're going to keep doing this until we're done with the join. So, chunk nested loops join, page-oriented nested loops join, and simple nested loops joins works for any predicate. But if it can be, we can have any predicate in our join, any join predicate, and we can use blocks nested loops join to perform this join. But if we have an inequality predicate, we can perform some clever optimizations that allow us to perform this join faster. And remember, equality joins are a super common use case for joins. So we can use what we learned earlier, hashing and sorting, to optimize these joins. And so a hash join uses a similar idea uses the same idea as nested loops joins, except that instead of joining chunks of a table or pages of a table, we're going to join partitions of a table. And how do we create these partitions? Well, we reuse the external hashing algorithm that we talked about earlier to create these partitions. And so now, for each partition of S, we're going to look at each partition of R, and we're going to join each of these partitions. And since we use a hashing algorithm, we can ensure that anything that would be caught by our equality predicate will be matched to the same partition. So first, we perform hashing on both our tables, and we create separate partitions. And as we perform the hash join on each pair of partitions, we run our join algorithm, and so we have partitions S and R. S is our outer relation. We reread S into memory, and as in chunk nested loops join, we stream R through memory. Yeah. So, do we want S to be bigger? What do people think? Should S be bigger or should R be bigger? So So the way we perform this join, right, is we have one table. For one table we read in a partition of that table into memory. If that partition does not fit into memory, remember, we're going to have to do another pass of hashing in order to make it fit into memory. We're going to have to recursively hash until our partitions fit into memory. The other partition, though, we don't have to read into memory. For the inner relation, all we have to do is stream it through memory, right? All we have to do is have an input buffer to stream all the tuples in that partition through memory. And so we only need one buffer for that relation. So the correct answer is our outer relation, those partitions need to be small enough to fit into memory. It doesn't matter for our inner relation. Okay, yeah. Yes, we also need an output buffer as we're outputting the join results. Yes. Yeah, that's right. Yes, the partitions from our outer relation need to fit into B minus 2 pages for this to work. Yeah. We read in each partition of S, and then for the matching partition in R, we stream that through memory. Yeah. All clear? Okay. All right, so remember the assumptions behind hash join. There's a maximum size for our outer partition. And if our partition is too large, right, due to some bad hashing algorithm or if we're unlucky or if our relation is too big anyway, then we're going to have to recursively hash. Okay. There's an optimization to hash join. It's called hybrid hash join. And it allows us to smooth out the performance of hash join. And the way we do this is we designate a special hash bucket, which we keep in memory. So as we're doing our hash join, it might be the case that we have extra space in memory. In this case, we can pre-hash part of our original relation by using this extra space, by creating a hash table in memory for this extra space, and by joining with our outer relation as we stream it through memory with this special bucket in memory hash table. Okay. Sort merge join is our other possible or optimization we can do on equality predicates. So the idea is we're going to sort S, and we're going to sort R first. And the key observation is that if S and R are sorted, then it's very easy to merge these tuples. It'll be kind of like the merge step of external sorting, of merge sort. So we first sort S and R, and basically we go through S and R, and for each matching tuple, we output it as we encounter the matching tuple. So we keep doing this until we're done with S and R. And our useful fact is that we never have to go back from S or back on R because we know that everything up to the point we're at is less than us in value. So when we're joining on an equality predicate, we don't have to go back and remerge things from earlier. Yeah. Yes. And that's a very good observation. So in sort merge join, every time we have runs of duplicates, we have to merge those runs of duplicates together. Now, what's the worst case of sort merge join? Yeah. Yeah. If we're joining on a column on R and a column on S, and all values of those two columns are the same, then this is really bad. We essentially degenerate into a simple nested loops join, because for every tuple in S, we're going to look at every tuple in R. And because our sort merge join, because our algorithm isn't intelligent enough to handle this case, we're going to degenerate into our worst case. Yeah. Good question. Any other questions? Sort merge join? Okay. We can also perform an optimization on our final pass. And this optimization is, if we observe that on our final pass, all we have to do is merge. Then we don't actually have to completely sort S or completely sort R. If all of these runs will fit into, if a buffer for each, if by reserving a buffer for each run, we can fit all of those buffers into memory and still perform the merge, then we don't have to completely sort S and completely sort R. Okay, any questions on join algorithms? Okay. All right, indices. So indices aid in data lookup. Basically, they allow us to search for things a lot more easily. And there are two kinds of indices, the clustered indices and unclustered indices. A clustered index has the pointers at the leaf pages of the index sorted the same way the data is sorted on the disk. So a clustered index will allow us to, by looking at our data entries, by looking at the order of our leaf pages, determine exactly what order our data is on disk. Whereas an unclustered index won't allow us to do this. For all intents and purposes in class, we're going to consider this unclustered index to have pointers that point essentially randomly on disk. Yeah?
For alternative 1, do we usually say it's always clustered with just talk about it?
Okay, so there are three alternatives to indices, alternatives 1, 2, and 3. And so the question that was, so alternative 1, in alternative 1, you have the whole data entry, the whole row, as an entry in the index leaf page. Whereas for alternatives 2 and 3, that's not the case. For alternatives 2 and 3, the entries at your leaf page are what the index is built on. Right? So when we build an index, we're going to build an index on some column. So the question was whether an alternative 1 index is clustered or not. And essentially, you can think of an alternative 1 index as behaving the same as the clustered index. Yeah. Okay, so yeah, we have alternative. So alternative. The difference between alternative 2 and alternative 3 is, if you remember from our from our section on text searches, we had postings lists, and those were alternative 3 indices. Alternative 3 indices are the same as alternative 2 indices, except we combine all the identical pointers for some value into one entry on the leaf page. Yeah. So we talked very briefly about ISAM trees. They're basically static B trees. You have some nodes, they contain some separators and pointers, and B trees or ISAM trees are really useful in looking things up. Yeah. Yeah. So alternative 2. So for an alternative 2 entry on an index, you're going to have, for each value of that index, you're going to have one, it's going to be associated with one pointer to some record on disk. Now, if you have many duplicates of records with the same column value, then these are going to be different entries in an alternative 2 index. In an alternative 3 index, this information is compressed. All the entries with the same value are going to be associated with that value. And you'll have something like the postings list. that we talked about in text search engines. Okay. Okay, so ISAM trees are basically static B trees. So I'll talk about B plus trees. So a B plus tree self-balances. And there's two key characteristics of a B plus tree: the fan-out factor and the degree. The fan-out factor is for some node, how many children does that node have? Right, so any node, remember any node in a B plus tree corresponds to a page in the index. And that node can contain some number of pointers. And for each pointer, we can follow it to find a child page. The degree is an invariant of the B plus tree, by which we maintain a minimum and a maximum number of entries in any page. So if our degree is D, then the number of entries in that page has to be between D and 2D. So every operation we perform on a B plus tree should preserve this invariant. And this invariant holds for all nodes except for the root. So for this tree, our fan-out factor is 5, our degree is 2, and the height of our B plus tree, is log base f of the number of leaves in our tree. So if we have 11 leaves in our tree, and our fan-out factor is 5, then the height of our tree is log base 5 of 11. Yeah?
So if the degree is 2, every node except for the root has to have between 2 and 4 entries, right? Well, there's a leaf node that only has 1,
So remember when we perform insertions and deletions on a B plus tree, right? It might be necessary, or it might be, so when we perform insertions to a B plus tree, if a node is too big, we have to split it. And you can remember remember from class, there's this algorithm for splitting nodes in a B plus tree. When that node is too full, we're going to have to split it and push a separator into its parent. And this might have to happen recursively. In case of deletions, it could be that, so deletions could trigger the opposite. A deletion might require us to merge nodes together. And this can be expensive. So an optimization we could do is keep some entries empty in case of deletion. Yeah. Good question. Any other questions? B plus trees? Yeah. So the degree is defined per B plus tree, and it's some invariant that we're going to describe to hold for that B plus tree. And that invariant is that for any node in our B plus tree, it can contain no less than D and no more than 2D entries. Right. So if we exceed these bounds, one way or another, then we're going to have some algorithm that splits nodes or combines them. And of course, we can tinker this in a real system. We can tinker with these with this behavior to optimize for certain things. But that's, in this class, we're going to be defining D as the order of the tree, yeah, as an invariant for that tree. Yeah. Any other questions? Okay. Okay. So, for example, if we perform a range query, 37 to 65, we're going to traverse these nodes. Okay. Another optimization we can do on B plus tree is compress prefixes and suffixes of these entries. Because the more we compress our nodes, the more entries we can fit in a B plus tree. So this increases our fan-out factor. Okay. Okay. So let's talk about query optimization. So having these physical operations, we can consider how to, for any given query, how to best fulfill this query. And there are three three different parts of optimization we have to consider. The plan space for this query, the cost of any one plan, and the algorithm to search this plan space. So our plan space we're going to define as left deep join trees. Okay, so we're only going to look at plans that correspond to join trees that are left deep. And we're going to look at, because our search space is too large, we're not going to look at trees that are right deep, or which are called bushy, which are neither left deep nor right deep, but say more balanced. And the useful thing about a left deep plan is we can read a relation into memory, and for each join, stream whatever we're joining with through memory as we're performing these joins. When we're performing these joins, so the biggest difficulty we have to optimize for is the size of our intermediate result, our intermediate results. So when we join two tables together, we need to find a good way of estimating how big these intermediate results are. And to determine this, we're going to use attributes such as the selectivity of a predicate or the sizes of our input relations to our join. And these are going to influence how big of an intermediate result we get when performing these joins. Okay. Any questions so far on optimization? Okay. And the last thing we have to consider in creating Query Optimizer is how we're going to search the plan space. And essentially what we're going to do is we're going to use a dynamic programming algorithm to search this plan space. So in our first pass, we're going to look at each table, and for each table, what's the most efficient way to access this table? After our first pass, the rest of our passes are going to be considering each subset of these relations, and for each subset of these relations, what's the best way to join what we already have with the new relation that we're adding in this iteration? Okay. Any questions about query optimization or execution? Okay.
Yours. Just need to paste it in.
All right, we're going to talk about briefly over SQL queries and just syntax that we think you should know after leaving this class. And the best practice I can suggest for you is to actually go into a SQL terminal, try it out, play with the FEC data set that we've had you do for the homeworks and go over the homeworks, because that's really the beef of learning SQL, and then you are expected to learn how this works on the exam. But the gist of it is you have a select clause where you're selecting the columns out of a table or multiple tables, and then you can apply functions on these columns. So you can apply aggregators like sum, count, and then you have to select what tables you're doing it from, add some predicates. You can group by things, order by things, and hopefully this is review. And just as a review of an expression, select albums.name, birth year. You can select columns out of multiple tables, and then the from statement there, albums and artists, does implicit inner join. And then the where statement is where your qualifier predicates are on what you want out of the expression. So the group by, a little caveat to it is that if you want to group it by, say, the artist's birth year here, you can only select things that were out of the things that you grouped by. You can still apply defined functions and user-defined functions in the select clause, so I can do count some other attribute, but if I want to actually display it, you can only select things out of the group by. And just for more syntactical things, in terms of outer joins, you just, in the from clause, you do table 1 full outer join with table 2, and there's a lot of different kind of joins. Well, not really. There's only inner join and outer join. There's also a left join, and question for you, what's the difference between a left join and a left outer join? Anyone? Trick question. There is none. So it doesn't actually make sense to have a left inner join. So there is no such thing as a left inner join, because inner join implies that both sides of the relations are matching to something. And if we want to do a left join, we kind of want the stuff on the left and the stuff on the right, we want it to be null. So this is a great Venn diagram of a bunch of different queries that I found on the internet. And the key part is, like, the outer joins down here for the full outer joins, it is able to produce something that looks like a Venn diagram where you have everything inside of the left side of the relation and everything on the right side of the relation, as well as everything that does match, and everything that doesn't exist in either the left side or the right side would be populated with null. And then you could modify your queries. There's a little example down here that if you want to only include the things that don't match, you can just have a little predicate that says A dot the join key is null or B dot the join key is null. So these slides will be posted, so have a look at this Venn diagram. Make sure you understand it. Just some more syntactical stuff with joins. All three of these different ways of joining are equivalent. Again, if you just put commas, it doesn't natural inner join, or it doesn't inner join automatically. That's the same thing as doing an inner join on some keys. And then lastly, natural join will automatically try to find all attributes that have the same column name and try to join them based on that. So in this case, sailors and reserves both have the key SID, and it would try to join them on that. Any questions on syntactical joining stuff? Great. And just as a word of note, you can do subqueries inside of SQL. And to walk through this example in particular, here we're trying to find all sailors who've reserved all boats. And just walking it from the inside out, that very inner statement, we're looking at one particular sailor, and let's call him Bob. Sailor Bob, we're checking if we want to find all the boat IDs that he's reserved. And then, so the deepest query is all the boats that some sailor Bob has reserved. And then the middle, I'm going from select B.bid from boats B, and where not exists, that query that we just ran. And not exists just checks if that subquery exists, returned any results or not. So performing the not exists on what we said was all the boat IDs that, all the boat IDs that Bob reserved, and this basically gets all the boat IDs that Bob didn't reserve. And then There's a lot of not clauses, so it might be a little bit tricky to think about nots. But the highest top level query is get all the sailors that have no boats reserved. So it gets all the sailors that has reserved all boats in the reservations table. When you're thinking about these queries, it's helpful to kind of think in the context of each subquery and then build up until you understand the bigger picture. I think working top down, it bends my mind. Any questions on this query? Yeah.
Is there a better way to do this?
There probably is.
Say I just select the count of the number of boats that each sailor serves, which matches the total number of boats.
So select the count of.
The boats that each sailor reserves, ever reserves.
But you would have to make sure that all the boats are all the boats in the boats table still, right? So we want to make sure that the sailor has reserved all the boats, not just. But you count them. Oh, so you count the number of distinct boats that they've reserved? Okay. There's probably a way to make that work. You need to compare that with the number of all boats. There's probably a way to do that. There's multiple ways to do everything in SQL. You could probably do this with a common table expression as well. But this is just one way of thinking about it. Any other questions? In terms of other set comparison operators, we just talked about exists. There's in, and the difference between exists and in is that exists checks if a subquery has any results. In actually needs something on the left-hand side, so I need to check if BID, some particular boat ID, is in a bunch of results inside of the subquery. Not in and not exists. They're pretty much the same thing, but negated. And then the any and all operator checks is similar to in that it needs a left-hand predicate. And you're checking that some value is either greater than any of the subquery or the results of the subquery, or all of the subquery results. Any questions on those extra set comparison operators? Yeah.
Is there an example for it?
Sorry?
Is there an example for it?
And so, I mean, if for example, you might want to check if your particular SID, like say we have a table of sailors, you want to check if where SID in, and then we do a subquery on SIDs, or just on the reservations table, and to see if it's in there, in the results.
Does the subquery have to select something that includes SID?
Right. Yes, it does have to. So the output of the subquery needs to have those values.
Oh, but not limited to SID, right?
That part I'm not sure about. Can you put in more information? I feel like it would break. I'm not sure, but you can try it out and find out. I have a feeling that would just break, though. You would just need to return that values that you're comparing to on the left-hand side and the right. Any other questions? So common table expressions I just mentioned. There's probably a lot of different ways to write that previous query. This is not the same thing, but you can have like a temporary variable, and hopefully you already have experience with this. Not much to say here. And lastly, I want to say a brief note about foreign keys. you can have them. Actually, that's pretty much all I want to say. You can have tables reference other tables with the foreign key syntax in SQL. Any questions on SQL syntax? And to go over relational algebra, it's just a mathematical way to express a lot of these queries. The key part that's different about relational algebra is that they're all set operations. There are no duplicates. And so we have the selection operator, which is kind of analogous to the where SQL syntax. We have the project operator, which projects some attribute out of a relation, and that's similar to the select in SQL. There's the cross product, which is essentially a inner join. There's the difference operator, which is similar to the except operator in SQL, the union, intersect, and then there's also a conditional join butterfly symbol, and that's essentially the join. Oh, I misspoke actually. So I said cross product, but cross product is actually the cross product, and there's actually a join operator in relational algebra. Yeah.
So since the operator symbols they eliminate duplicates, it's not exactly the same as the
Not exactly the same, right? You have to think in terms of sets when you're dealing with these operators. So just as an example of translating SQL, so I mean, you can't always match. You can't really say that this is completely equivalent to the SQL expression, as you just pointed out, because of the distinctness. But if there was a way to convert this into like relational algebra, this is the closest representation we could have of what's going on.
Do this in the mindset of having all distinct.
Yeah. So here we're selecting annual income from all the people and we have a people's table, we have an income table, and we're matching it based on Social Security. And that's just basically projecting out the annual income field, and then we're selecting on this cross product of the two tables, P and I, or the people's table and the income table. Storage.
Okay, so we're going to talk about storage. So we're going to talk about the file formats that you're storing. So for your pages, so this is one page, for example, for fixed length records, the packed format is when you keep all of your free space at the end, so all of your records are going to be at the top, and then every time you remove something, for example, you're going to need to fill in that space. And at the very end, so you see N right there at the left, or your right, is the number of records. So now when you want to insert a file in that page, by knowing the number of records that you currently have in your page and also the size of your records, then you'll be able to find the offset at which you're supposed to put your next record in the slot. So we also have, for fixed length records, we have unpacked. So now, instead of having all of your free space at the end, you can have it throughout your page. So at the very end, now you need to keep track of a bitmap, and basically this bitmap is going to be equal to, the number of bits will be equal to the number of slots that you can hold in your entire page. So here, for example, you can have M slots total, so you will have M bits in your bitmap, and then each slot will indicate whether or not, so if the bit is 1, that means that there is currently a record at that slot. So if you wanted to insert a record inside your page, then you look for the slot which has 0 for its bit. And now we have variable length records, so now your records don't have to be the same length, and in this case, we also try to keep your free space at the end, but now all of your records can be stored at different locations. So for example, the very first slot isn't necessarily the very first thing inside of your page. So at the very end, you also keep track, similar to the bitmap, but now for your slots, you actually keep track of how big that record is. So for example, here we have, for slot 1, you have 24 bits, and it will have a pointer to where that record is in your page. And you also keep track of the pointer to the start of free space, so every time you need to insert something, you just use that pointer to go to where you need to insert your records. So that is basically it for file formats. Does anyone have any questions? It should be pretty basic. For the final, the most you should really know is to be able to understand this, but also be able to calculate how big your tables or your pages need to be. So how many bits you need to have in a bitmap, for example, or depending on what information you're storing, then you need to know how many records you may need to have in your table. So we're going to quickly go over cache replacement, and this is going to be for review for everybody, especially for those in 162. So the buffer replacement policy, basically, you follow buffer replacement policy to decide which pages you want to replace in your buffer. So the policy can actually have a very big impact on your I/O. So for example, for least recently used, so this is when we're replacing the page in your buffer that was least recently used, you run into a problem that's called sequential flooding. So that happens when the number of pages in your file, so you're reading your page over, or your file over and over, and the number of pages in your file is greater than the number of pages in your buffer. So for example, here we have our example of sequential flooding. So we have our access method at the bottom. These are all of the pages that we want to read. So our cache is cold, so you just load everything in. And then now you want to read F, but now we have a cache miss. So you replace the very first item, and then so on. So you can see A will then replace B, and C will replace B will replace C, C will replace D, and D will replace E. So now every page request has resulted in a cache miss. So that's the thing to note when you're looking at LRU. But MRU, which is basically the opposite, so now instead of replacing the page that was least recently used, we'll replace the page that is most recently used. So this fixes sequential flooding. So here is our same example from before. So we've loaded in everything into our cold cache. And then now we want to access F. So F will result in a cache miss and will replace the most recently used, which will be E. But then now you see for the rest, so A, B, C, D, those things are already inside our cache and we won't replace them. So now when you want to find A, you will have a cache hit, and so on with B, C, and D. Any questions about LRU, MRU? So clock replacement is probably the most difficult out of all of the buffer replacement policies you will need to know. So for clock replacement, you can think of having all of your pages in a circular list, and then you will think of having a clock hand that will be at one page in that moment in time. So each page also keeps track of another thing called a reference bit, which we also call the second chance bit, which you guys will see in a second why it has that name, and it indicates if that page has been accessed. Also, another thing for midterm 1, a lot of you guys were really confused about what unpinned meant. So pages are pinned when a program or process is using it. So if a page is pinned, then that means you cannot replace that page, even if, for example, it was least recently used in your cache. So all the examples we have, so in the midterm, in the discussion, and the examples we just went over now, it's assuming that all those pages are unpinned. So just make sure you guys know that if a page is pinned, then you can't replace it. So moving on with clock replacement. So what happens when you have a hit is that if the page is inside of your cache, then you just set that reference bit to 1. So for example, if the page after where our clock hand is a hit, then you just set the reference bit to a 1. And an important thing to notice is when you have a hit, you don't move your clock hand. So on a miss, what happens is now you will keep moving your clock hand until you reach a page that has a bit of 0. But along the way, when you go past a page that has a bit of 1, you will change that bit to 0. So what that means is if we have one miss here, so what happens is that right now, so if we have a cache miss, the page you'll want to replace is the one that the clock hand is currently pointing to. So you will change that bit to a 1. But for this semester specifically, after you have a cache miss and you move your clock hand to the page that you have just replaced, then you'll want to move your clock hand down 1. So here you see if we have our cache miss, we change that to a 1, but we also move the clock hand down 1. And you don't change it to a 0 yet, even though, so in this case, our clock hand is pointing to a page with a reference bit of 1. We don't change it yet. So now, if we look at the case where we have another miss, what will happen is that this clock hand will go down to the page after, which has the 0, and that's the page it's going to replace. But the page it's currently on, it will change that reference bit to a 0. So it will change that to a 0, and then you'll move the clock hand down to the next page, and you'll replace that page, change that bit to a 1, and then you'll move your clock hand down 1. And that is actually all I have for cache replacement. Yeah.
So if the page is pinned when the reference bit is 0, and after it's unpinned, do we change the reference bit back to 1?
So in that case, I believe you would still change the reference bit, but the thing is that if you go to a page that is pinned, and then
so like if we pin a page that is 0 for the reference bit,
yeah,
and after we unpin it, do we reset the 0 back to 1?
do you guys know? So if he's saying so if you just unpinned a page, then what do you set the reference bit to? I think you would set it to 1. Right?
Set it back to
Yeah.
1.
Yeah. Any other questions? Okay. That's it. If you guys have any questions about any other topics in the class for the last 15 minutes or so, you guys can come up and ask us.
Any more questions on any of this material?
I didn't talk for 10 minutes. I talked for like 45 minutes. Do you think you can explain the three alternatives really fast?
Yes. Okay. So
We have a system like index. We have relations that have some bookkeeping. And let's say we have R, this relation R, and we have two columns, A and B. And index is so in alternative. So let's say our these are here. I'll leave them.
Oh, so these are the.
We want to undo. So alternative one would mean that alternative one would mean that our entire tuple fits on our leaf. So if it's sorted on A, right, I'm gonna have 1, 2, 1, 3, right? 2, 3, then the whole point is 4. So you don't know the current state. 3, 1, 4, 5, something like that, right? That's an alternative one index. Okay. So an alternative 2, right? So an alternative 2. We're going to instead of having a full tuple, we're only going to have what the index is on. So the index is on A, right? So we're not going to have any B values or anything else. So if you were tuples, alternative 2, right? So the tuple was the state of these two, but what was that specifically for the key? Talking about what alternative. Yeah, this is alternative 2. Alternative 3. So alternative 3, we have key, and then a list of all the pointers that are associated with the key, right? So all of 1 is okay. All of 2, we're just compressing. But if
they're different arrays. Yeah.
Super question.
I mean, so
What does
like this CEIL? It's the ceiling operator. It's kind of like that. So like if we have 4 divided by 2, that's 2 with no remainder, right? So same thing. It's rounding up. So 5 divided by 2 is 2.5. So yeah, so this is seal. Then we seal makes us 3, and then phase figure out.
And 1.1 is
1.1 becomes 4. We just round up. And from there, we want to make sure that all escrow changes that we want.
I can.
Which slide would you like to go back to? Oh, next one. So redo phase. All the traces back. Figures out, makes all the changes.
Yeah.
like when she was saying that specifically for this semester, something, I don't know what types of
Yes. So on a this is always. Yeah. Go ahead.
Based on let's say if these two are basically these two different things, they're still so like what I do
these are persistent like this at this time. The checkpoint begin not in checkpoint.
Okay,
So the first thing you check is
yeah, so let's say
To redo it, just to make sure it's consistent. And then the last one is once we've done it, to all transactions that didn't end. So this is going to be here. There's going to still be some transactions running. We don't want to.
Yeah.
We can't continue them.
Yeah.
And then it's supposed to happen.
And then for a pinned and unpinned, do you just skip over a pin page?
Yeah. Any pin page, pretend it's not there.
Doing everything for these transactions.
If it's pinned, we pretend it's not there. Yeah. Yeah. Pinned for when we're talking about buffer replacement policies, we only care about pages that we're going to replace. If we're never going to replace it, then yeah, that's right.
And our goal is now to reverse
Yes.
so redo is to make sure
On a hit, in a hit, you don't do anything. In the hit, the only thing you do is set the bit. Yeah.
now we're up to after redoing all the changes as reflected in the pages
Here's just our way of keeping track of what's running. They're meant for
On a hit, so on a miss, right? Yeah, you check it. If it's a 1, set it to 0, and if it's 0, replace it.
person, what was the update to that page?
either set it to 0
and then we undo
So if we set it to 0, we have to move, obviously, because we're not done yet. We keep moving. The second we replace something, we move it one last time. We move it one last time so we don't immediately, reset this. And this for this class.
Went all the way down, went past, and it crashed here, so it never actually finished. So when we redo it, we know for sure now.
Can you explain the difference between P equals 3, general worker,
Yeah.
and that 2A?
I would go. So let me double check with you. I think. Yeah.
Things that were still running or source.
and then once we right that makes a ton of sense.
But basically, you're trying to clean up the state.
And then so
Well, it seems like really different from that.
cool. Awesome.
Did you ask me about the 2A?
Yeah. So I guess so what I we're talking about like 3 in general with 3 plus 3. I guess like the main difference is that you read into 2 and you leave in the 2 or stable with the output. You read in 3 and then you have the 2. So you have the
So
What's the difference in pass zero? In pass zero, I mean, basically the two-way is kind of really rudimentary version, where you're not utilizing all buffers to do that pass zero sort. So what is in two-way? I believe it just reads each page. I think it sorts it. Yeah. So it just reads one page.
I mean, this isn't a detail that you're going to really need to hear about, I imagine. The idea was that, in past zero, right, what we want to do, in the full algorithm is read everything in your memory, sort that, and then write it as a sorted run.
Yeah.
I think when we were talking about it in class, when we were introducing sort, we were introducing it, self-page granularity. So I think the idea was read a page, sort that page, write it back as a sorted run. Just have runs of one page big. But that's obviously not the
For v equals 3, then you